Go. Hello everyone, welcome to the third day of the IChemE Student Summit, yesterday, today and tomorrow. We acknowledge the traditional owners of country throughout Australia and recognise their continuing connection to land, waters and culture. We pay our respects to the elders past, present and emerging. Today, the session will be focused on sustainability within chemical engineering, and we'll be joined by 4 academics who will discuss their work across alternative energies. As we begin to address anthropogenic climate change, a switch to sustainable energy generation is needed, and for efficiencies of these technologies to be improved to meet the global demand. First, Professor Rose Amal from the University of New South Wales will speak about Power 2X. Professor David Lewis from the University of Adelaide will talk about biomass to biofuel conversion. Constantine Tsounis from UNSW will speak about the startup he co-founded called Switch2, before we see Professor Paul Downhower's presentation about sustainable carbon, which is pre-recorded from the University of Minnesota. Rose, David and Con will then answer questions about alternative energies from the audience. Before we start, I'll hand over to Olivia to reintroduce Rose and then we can get started.
Our first speaker is Rose. She is the leader of the Particle and Catalyst Research Group in the School of Chemical Engineering at the University of New South Wales. She's also been listed in Australia's top 100 most influential engineers from the years of 2012 to 2015. She's received the Companion of the Order of Australia for her service to chemical engineering. And in 2019, she was awarded the New South Wales Scientist of the Year. She'll be talking to us about Power 2X. Over to you, Rose.
Thank you, Olivia, and thanks, Tom. Well, first, I'd like to thank all the organizing committee members for giving me this opportunity to speak to you this afternoon. And I really like the theme that the IChemE Student Summit sort of choose chemical engineering yesterday, today, and tomorrow. In fact, that I gave a few lectures and talks the last couple of years under this theme, but it's a bit different. Chemical engineering, past, present, and future, or chemical engineering, future of chemical engineering, learning from the past. So it's sort of under that, and it is actually a good way of reflecting what's the past and then how to learn from the past to make sure that we becoming a better chemical engineer, present and the futures as well. So I think that when we're talking about chemical engineering or past of chemical engineering, history of chemical engineering, you always heard about the name of George Davis. And I'm sure that during these last few days, you already heard his name and about the birth of chemical engineering field back in 1887. So I think I just want to stress that again, is that we can learn a lot from our past. So our present is shaped by those who came before us, and our future is also, we learn a lot from the past and the present times as well. And as a chemical engineers or chemical engineering students, I'm sure that you heard about Haber-Bosch process. If you don't, then you need to make sure you go and check it, because you will not be able to graduate chemical engineering before knowing Haber-Bosch process. Because this is probably the most significant breakthrough of chemical engineering. And it is actually a process that changed the life of everybody in the world. And is a process that requires a lot of energy, but then it's a process that sustain the life in our planet. That's the reasons that why we have 7.8 billion people now in 2020. And the process of the Haber-Bosch is actually developed back in 1900. So at that time, we only have 1.6 billion people, and it's grown. And thanks to the ammonia that produced from the Haber-Bosch process. And so today, when I'm talking about energy, I think it is important to sort of reflect on this process. And the reason is because that this particular process require a lot of energy. And therefore, that as a chemical engineer, we need to rethink about in terms of how to develop more sustainable process to make sure that we have a way of life and process that are sustainable, and we will be able to make a better future. And I like to also put this this slide. This slide was taken from the ChemEng Matters, Chemical Engineering Matters, just to stress that chemical engineering does matters. The process that we learn, the process that we develop, that is actually used in terms of our daily life. And last couple of days, you talk about water already. So we're talking about chemical engineering process is very important for solving the global challenges. And the global challenges are, as you can see, there's 4 things that it's already on top of there. It's the water, energy, food and nutrition, and health and well-being. And again, chemical engineering is a vital part of this jigsaw of our 21st century living. Today, my talk, and as what Tom had already mentioned and Olivia mentions, Power to X, and also another way that I can call it is that probably harnessing the solar energy for chemical processes. Since the beginning of my research career, I always passionate about looking at research for sustainability. So when I started my career, I was looking at how to develop chemical processes that can solve our environment problems. So that's why I was working on water purifications. And then the science and the principle can actually be used also for energy applications. So that's sort of how I sort of started my work in energy. And when we're talking about sun, I know that we all know it's that although sun is 150 million kilometers away, is nuclear reactors. The energy we can even feel, and we can actually see. We can see the brightness, and we can feel the heat 150 million kilometers on the planet. And it's free in a sense that we can harness it. It's always there. We know that in the morning sun will rise and then set, and it will go on and on again. And electrical engineer has been very good in terms of capturing this, harnessing the sun energy and convert it to electrical energy. And we have a lot of now in Australia, I think 2 million homes actually have the solar panels. So as a chemical engineers, then we're looking into how we'll be able to harness this solar energy and convert to chemical energy. And as shown on the diagram up there is that we have the solar energy have a wide spectrum. The UV, it has a wavelength at a short wavelength, and also visible light, which is we can see it, and also the heat is the infrared part of the spectra as well. So when we're talking about how to harness solar energy to convert to chemical energy, then we can harness the photon, the light part of it, and we can also harness the thermal, the heat part of it. Or other ways is that the photon and thermal, and we can convert it to electricity, and using the electricity and convert to chemical energy. So we can, what I'm trying to sort of say is that we can harness the light and harness the heat and convert those energy to chemical, or we can indirectly convert the heat and the light to electricity first, and then using the electricity to convert it to the chemical energy. So my research is sort of encompass those things. We're looking at the harnessing the light straight away, which is known as the photocatalyst. So we're using a catalyst in order to harness that light, or we can use a catalyst to harness the heat of the sun, and then use that heat in order to drive the chemical reactions. Or as we can see from this diagram here, we can harness the light and then convert to electricity, and then using the catalyst again in order to drive the chemical reactions. And in the research that I'm doing, I'm actually looking into designing catalyst materials. And I'm fortunate the animation doesn't work. Is that what I'm trying to explain is that there's a lot of ways. Again, that's the chemical engineering skills are very important. There are a lot of ways that we can make catalysts. And one of the way is the flame synthesis, which is I can use the flame as the reactor in order to make the particles. And the design of the catalyst is very important, because the design of catalyst is one of the key in terms of how to effectively harness the sun energy in terms of convert it to chemical energy. And this particular one is it's a reactor system that we have. It's actually designed by Todd, which is the speakers, the third speakers for this session, and at harness solar energy in order to degrade dye. But the same reactors also, we can use it in order to convert water or convert waste in terms of to make hydrogens as well. So as a chemical engineers, our research or our work is not just in terms of designing the catalyst, but also we have the skill to be able to make design the reactors and build the reactor system as well. And it's very important, because with that is to actually differentiate us from chemists or from material scientists, is that our capability also to be able to design a reactor system in order to be able to really drive the reactions effectively. And other ways in terms of harnessing solar energy in order to convert it to chemical energy, for example, to make hydrogen, is to looking at the converting the biomass, to converting waste materials and to extract hydrogen out from it. And again, we can use sunlight to do that as well, either using the sunlight directly with the catalyst in order to extract the hydrogen from the biomass, or I think when we were talking about the other process, which is also using sunlight, but using the sunlight to generate the electricity, and using the electricity and the catalyst to convert the biomass to hydrogen as well. So again, we're looking at using the abundant sun energy or renewable energy, and then using our chemical engineering processes and designing catalysts to be able to extract the hydrogen. This is another project that we have. And when I talk to normally energy people or electrical engineer people, we talk about this as a power to X. What it means that we're using renewable power and using the power and using the energy of the renewable power in order to make X. And X could be anything. And this X for this particular process is methane, natural gas. But if I talk to chemical engineers like us, is that I call it as a sustainable chemical process, which we're using integrated solar electrolyzer and solar thermal catalyst in order to produce methane. And if you look at this particular diagram here, I'm not sure you can see my cursor, but the right side of the diagram, what we have, this is what we have in the red box. So in the red box, we have the recharged batteries, we have the solar tractor, we have the water electrolyzer. So we have the solar panel, which is here, that will be able to harness the solar energy and convert to electricity to drive the electrolyzer. So the electrolyzers will then convert water into hydrogen. And the hydrogen then will be pumped into the reactors, which is then will be heated up by the heat from the solar collectors. And that can goes up to temperatures of 700. For this particular reactors, the temperatures only goes up to about 400 degrees. And with the nickel catalyst that we have, we can convert the carbon dioxide, which is again can come from the air that we capture, and the hydrogen that coming from water to produce methane. So if you look at this particular process, what I want to sort of say is the ingredient is mainly water, carbon dioxide, which is a waste that we wanted to also get rid of, and the energy coming from the sun only, and that can be used to produce methane. Methane, as we know, that is also a chemical product, a chemical building blocks for a lot of chemical industry as well. And methane is also a gas that is very important for energy purposes as well. So if you look at that, that is one of our power to X example, but it's harnessing the heat and also the light of the sun in order to drive the reactions. Another project that we have is looking at harnessing the solar energy to convert the electricity as mentioned, and then drive the catalyst process in order to produce hydrogen. And again, a lot of our work here, we normally just focus on to make hydrogen in this case. And a lot of process that we focus on is to make active and selective and stable catalysts. So this is sort of the key things that is important in chemical industries. We have to be cost effective and has to be also stable and selective for the chemical reactions we want. And when we talk about processes as well, we have to also think about, again, the sustainability. And in most cases that the fresh water, especially in New South Wales, is a precious commodity. So when we're talking to the industry, one of the things that, okay, you want to use water as your raw materials, do you have the water? So that is one of the problem. But we have plenty of seawater, especially Sydney, you know, you live quite the coastal area. So we're also developing, looking at how to convert the seawater and using seawater as our source to making hydrogen. And again, the designing of the catalyst system is very important because seawater is much harsher than the others. So talking about the work that we're doing now, it's the few examples, the unit operations that I mentioned about that. You can see that that's a lot of those things that you can also using it to convert other small molecules. I mentioned about water already in some of the slides, using water and convert water using electrolyzer to produce hydrogen. But you can do the same thing with the CO2 as well. So you can use the CO2 as a raw product, and we also have process which is using the electrolyzer and our catalyst. And the electrolyzer is driven by a solar panel, and then convert the CO2 to, for example, syngas, and also to convert to formic acid as well. And this is very important because I think this is the future of the chemical processes, is to looking at converting the small abundant molecules to chemical products rather than rely on fossil fuels. A lot of the things that we're doing currently in chemical industry, we rely on fossil fuel, for example, in order to make syngas, or steam methane reforming to make hydrogen. But again, we can look into also some other things that we have abundance, like the carbon dioxide that is come out from chemical industry. And by doing that, we can actually close the carbon loop as well. So I think it is important for us to really looking into what is we can do in the future and utilizing our renewable power. So the beginning of my talk, I mentioned about Haber-Bosch process, ammonia synthesis. So this process has been there for a long time, for more than 100 years. So the process, which is yesterday for 100 years and also still today, but it's a technology of yesterday. How they get the ammonia is that they get the hydrogen from the methane, the steam methane reforming. And that is, again, the methane is actually coming from fossil fuel. The nitrogen is coming from the air, so that's fine. Today's technology, which again, a lot of the industry started to look into that, is instead of using the methane as to extract the hydrogen, they're looking at using electrolyzer in order to get the hydrogen. So the hydrogen is coming from the electrolyzer, and the hydrogen then will react with a similar process as what the Haber-Bosch process is in order to produce the ammonia. So in that way, that instead of using fossil fuel, now we can use a clean, green hydrogen in order to make our ammonia. And what I see, though, that in the future is that the tomorrow way of making ammonia in order to sustain life is that we can also using the nitrogen, but instead of have to use high pressure, 200 atmosphere, high temperature, 450 degrees Celsius, we should be able to use electrolyzer, or you can use the renewable power and operate at a sort of a low temperatures and low pressure in order to convert nitrogens and water and using the catalyst in the electrolyzers to produce ammonia. So this is something that I foresee that perhaps in not immediately tomorrow but tomorrow in terms of maybe 20 years times or something, and something that the chemical engineering students here probably will be the one who develop this further. So with that, I'd like to thank you, and I also thank my members, including Con, who is part of this the group members for looking. For me, you know, I consider sometimes I'm the past as already, and then I think my group members is the present, and then you all, then the audience, is the futures of chemical engineers, and I think that for that I believe that the future is bright. This particular quote is from Svante Arrhenius. I think you all know Arrhenius equation. Arrhenius equations is equations to relate the reactions rate constants with the temperature. In 1900, he mentioned about humanity stands before a great problem of finding new raw materials and new sources of energy that shall never become exhausted. In the meantime, we must not waste what we have, but must leave as much as possible for coming generations. It was supposed to be animation here, and with the animation, I was not supposed to show you Arrhenius first. I was supposed to show you the quote and get you to reflect that this particular quote is actually very relevant for today's, and I'm sure that it's going to be relevant for tomorrow. But it's actually a quote that was Svante Arrhenius sort of posed about 200 years ago. And with that, I'll end my presentation, and thank you. So now I'll pass it back to Olivia. Olivia? No. Is it?
Okay, it looks like I might.
Maybe it's you, David.
Okay. Thanks very much, Rose, for your great talk. So I'm going to talk to the audience about renewable energy, in particular renewable liquid transportation fuels. And to steal Rose's thunder, she had power to X. I think I should call my talk waste to X. So it's on a similar line where we're trying to develop sustainable processes and technologies for producing energy. I began my interest in renewable fuel in 2007, and I was looking at growing microalgae as biomass for biodiesel. It was a great project to write research papers, but commercially irrelevant. It's very expensive to grow microalgae, and why would you turn it into fuel? There's much better products you can produce from algae than fuel. So we still rely on a lot of liquid transportation fuels. Australia consumes around 20 million tonnes of diesel per year. And if you think about the consumption of diesel is such an important fuel in our life because of all the transportation. So all of our trains and trucks require diesel. And unfortunately, we import most of the diesel that we use in Australia. But how can we make this more sustainable? So we could look at biofuels. So if we look at waste, we produce millions and millions of tonnes of waste annually. And a lot of this waste is organic rich. So these organics we can actually turn into crude oil through a hydrothermal process. And I'll talk more about that in a moment. But waste costs companies a lot of money to manage. So what I'm trying to do is find a solution where we can turn waste into a valuable commodity, but also reduce overheads of companies by them being able to avoid to dump their wastes. So basically we're trying to close the loop and turn waste into fuel. There's a small picture there with Sydney with a pile of car tyres superimposed on it. That just gives you an idea about the volume of waste that we produce in Australia. So you can imagine what that pile would look like if you looked at the global waste production. Okay, so I might start with the first 3 laws of biofuels. So basically, this is probably relevant for most renewable energy. It's not really renewable or classified a biofuel if it's not energy positive. What that means is that you need to use less energy to produce the fuel than you get by using the fuel. So it needs to be energy positive. Interestingly, a lot of crude oil products are energy negative because the extraction cost is so high energetically, and converting the crude oil to a fuel and burning that fuel is actually energy negative. So we need our biofuels to be energy positive. That's a big challenge. Another challenge is the carbon footprint. To be a biofuel, we really want the carbon footprint to be less than a fossil-derived equivalent fuel. In the US, lots of market research has been undertaken to test the market to see if people would buy biofuels. When the biofuel was at a higher price than the fossil fuel, not many people bought it. When it was at cost parity, the same cost, many people would prefer to buy the biofuel. So the cost and the carbon footprint are very important. And basically, it's got to make money. So a company is not going to use or produce biofuels unless they can make a profit. This is the big challenge. So what's a good feedstock? So we've been looking at hydrothermal liquefaction, which is a high temperature pressure reaction that we put organic material to a high temperature of 350 degrees Celsius and a pressure of around 200 bar. So we take the wet biomass to just below the critical point of water. Through the heating curve to that point, we get depolymerization of the organic materials and they reform into a crude oil-like product. So it's a very interesting process, very complicated, but it will turn wet organic material into a crude oil that can be further refined. So I mentioned before that we were looking at microalgae as a feedstock for biofuels. It's too expensive to grow algae for fuel. But during that journey, I came across hydrothermal liquefaction, but we also came across biosolids. So biosolids are dried municipal wastewater sludge. So during a conventional wastewater treatment process, we grow bacteria to remove soluble organic material, carbon, beg your pardon, from the wastewater. So we grow the bacteria in the water to clean the water, but we produce biomass. This is called sludge. And the sludge has to be removed from the wastewater treatment process, and it's a big waste problem for the industry. The waste is very toxic because it's grown in municipal wastewater. Depending on the location, it may be full of heavy metals, and it's very expensive to dispose of. So around the world, there's many different techniques to manage this waste. In England, they incinerate it. So the waste, as you can see on the diagram, is produced around 2 to 2.5% solids. So it's very dilute. In the UK, they incinerate that waste. So you can imagine the energy cost with all that water. Some countries dispose of the sludge to land, but the EPAs around the world are starting to stop that because of the contamination issues, and it also goes to landfill. So it's a big problem. So Melbourne Water have stockpiled their biosolids for many years, and they have around, I think it's about 1.6 million tonnes of biosolids stockpiled in Werribee. So we were asked to look at those stockpiles to see if we could make a biofuel from them. So this gives you a couple of pictures of these stockpiles. So they're very black in colour, very fine material. You can see the sluice there with some fresh sludge being pumped into a drying pan. So that black water is about 2.5% solids. It's pumped into very large drying pans. It's left there for about a year for the water to evaporate, and then the remaining sludge is scooped up and stockpiled. So these stockpiles are massive, and they self-combust in summer because they're so full of energy. Typically, they're around 40% inorganic material, but the older stockpiles get as high as 70% inorganics. So they're quite variable, but full of high-energy organic material. So if we look around Australia, biosolids are produced all around the country in different volumes. The economics, really, we need to be looking at the larger stockpiles to consider converting those wastes to a fuel to be economically viable. But globally, it's a massive opportunity and a massive problem. So the industry spends around $100 million per annum just managing biosolid waste. So it's a great opportunity to come up with a new waste management tool, but also to convert this waste into something useful. So the challenge that we've been undertaking for the last few years is trying to develop a technology based on hydrothermal liquefaction that is scalable and can take this feedstock and convert it into a renewable crude oil in a continuous process. We've worked at different scales from bench to pilot to commercial demonstration, and the economics so far, we would require a tipping fee of around $160 per dry tonne of biosolid waste. So I showed you a picture where the materials produced around 2 to 5% solids. So you can imagine to get a tonne is going to take a lot of litres of the sludge waste to get that tonne of biomass that would require only $160 to be paid to dispose of it. So it doesn't sound much, $160 a dry tonne, but it is a lot of money for the industry. So if we were to just convert this biomass into oil, the economics probably wouldn't stack up. So we need to look at valorizing all of the product streams, and I'll talk a bit more about that. And another economic reality is business are interested in this technology, but businesses nowadays would like a return on investment in a period of 5 years or less. So that's a big challenge. Investors want their money back as quickly as possible and are not interested in long-term investment where the payback is greater than 5 years. So that's quite challenging. So the process that we've been working on is intercepting the biosolid feedstock. So intercepting the waste at the source. The picture there shows the drying pans at Werribee. You'll see later there's a different process in Queensland where they actually use centrifuges to thicken this waste, add a polymer and produce a 20% solid waste stream. So we need to intercept, we need to form a suspension and thicken the waste. Then we would pump this thickened waste through a hydrothermal liquefaction reactor. The picture there, where you can see a couple of tubes, that was our pilot plant that operated about a tonne a day. We are now building a plant that's about 2 tonnes per hour. So we've scaled up quite a lot. I'll talk more about the scale in a minute. So in this continuous hydrothermal liquefaction, you can then convert the organic materials into a crude oil. But one of the challenges of putting these types of waste through hydrothermal liquefaction is it's not just organic material. It's all the inorganics. It's all the heavy metals. So you've got quite a contaminated aqueous phase post-HTL that needs to be managed. And you have to separate the crude oil from that aqueous phase, which also is not trivial. But once you've separated the oil component, that can be readily refined in the standard refinery processes. So we're currently funded by ARENA to build and operate this demonstration plant. Our industry partner, I should have mentioned it before, is Southern Oil Refining. So this company is based in Wagga and they have an oil refinery in Gladstone, Queensland. Their business was built on waste to value. So most of their business is recovering dirty lubrication oils, removing the contaminants, and reselling the lubrication oil back to the market. So lubrication oils don't lose their lubricity when they're used, they just become contaminated. So you can imagine in Australia, we use a lot of lubrication oil in the mining sector and the heavy transportation sector. So Southern Oil is about $100 million business, and they are quite successful at recycling waste oils. One of their wastes is dirty fuel. So they got interested in renewable fuels to add value to their dirty fuel that they recover from lubrication oils. So I've been working with Southern Oil for a few years now, developing the hydrothermal liquefaction technology for managing the biosolid waste streams. So one of the challenges about developing new technology is what we call the valley of death. So at universities, we have a great time, we get research grants, we can do wonderful things, but we work at early development stages. So we call it technology readiness levels. So it's a term that we've plagiarized from NASA. So they talk about TRLs. So TRL1 is pure research. TRL9 is when you're about to go to commercialize your technology. So as researchers, we work around TRL 1 to 3. And once you start getting to TRL 3 to 4 to 5, you really need to be working with an industry partner. And ideally, you would have a startup company. So the risk is with a startup company, you need investment, but you're still doing R&D. So the returns on investment on the startup are very minimal for the early years. And that what happens as you scale up your technology, you enter what's called this valley of death. So this technology gets bigger as you go from bench to pilot to demonstration, but you're not big enough to return any profits. So it's very, very difficult as you go down that red line on my chart here of maintaining investment to run your company to develop the technology that you want to commercialize. Once you get to this commercial scale production, then you can start making a return and obviously make a profit, and then your company is successful. So many, many startup companies go into the valley of death and never leave the valley of death, and you never hear of them again. It's very challenging. Fortunately, in Australia, we have ARENA who fund projects in the valley of death. The government realizes that to get private investment to develop new technologies is very difficult in Australia. So they've created ARENA many years ago that will fund renewable energy projects through that valley of death. So where we're at with our technology, as I mentioned, we've scaled it up to demonstration scale. The picture here is biosolids produced at Luggage Point in Brisbane. So these biosolids have been centrifuged with a polymer, and that what you see there is about 20% solids. So still 80% water, but it has a rubber consistency. Urban utilities have produced this particular waste. They send that to landfill. So every day, B-double trucks are filling up with this waste, going off to a landfill to dispose of this waste. I believe they pay about $130 a wet ton. So they're very concerned about us needing $160 a dry ton to make hydrothermal liquefaction viable to manage their waste. And this is why we have to look at other products in addition to a renewable fuel. So we're looking at these different biosolids wastes. We're looking at how do we integrate hydrothermal liquefaction technology into a standard wastewater treatment plant. We're looking at the effect of the polymers that the industry uses and how does that affect the oil quality. As I've mentioned, in the 20% solids, you've got 80% water. We don't want the water. So what do you do with this aqueous phase once you've produced your crude oil? And I should mention about 50% of the organic fraction will convert to a crude. So you can imagine there's a lot of other products that we need to valorize. And one of the issues is the aqueous phase because there's so much contaminated water coming out of HTL. And then we have to really look at these co-products. So I've got about 8 PhD students currently working on the different areas of research around HTL. We're now very much interested in catalysts that we can add to the HTL reactor to improve the quality of the oil, to remove heteroatoms such as nitrogen and sulfur, reduce the acidity, etc. So there's still a lot of R&D to be completed with HTL in parallel to scaling up the technology. So I'd like to conclude my talk. And I'm sure Rose is the same, she said this, that the young chemical engineers, which is you, will change the future. We need you to design and operate sustainable processes. And as you know, it's getting harder and harder to get career jobs nowadays. So really, as young engineers, you need to create your own jobs, create your own companies. And the solution is if we can produce cheap, clean, renewable energy, this will drive the future economies of the world, and I think that is your challenge. So that concludes my talk. Thank you for listening. Over to you, Constantine.
Wales. He has co-founded SwitchH2, which is a rapid research commercialization startup with the aim of converting industry waste into hydrogen. He recently got first place in the Peter Farrell Cup, the University of South Wales entrepreneurship competition. He'll be talking to us about his startup, SwitchH2. Over to you, Constantine.
Thanks very much, Olivia, and it's a great pleasure to be here So my name is Constantine, as Olivia mentioned. I'm going to be talking about my topic, Brewing Up Energy, which is really about our journey with our startup called Switch to Engineering, in translating some of the technology that I do part of my PhD in the Particles and Catalysis Research Group, where I'm supervised by Professor Amal, who you would have saw talk earlier. And so I guess over the last couple of days, you've probably been bombarded with so much technical knowledge about chemical engineering and industry and what that sort of entails. So I thought for this presentation, I'll give you a little bit more of a student perspective, sort of what I'm doing now, how I got to what I'm doing, and just sort of an overview of our technology. And so just very quickly, a little bit about myself. So I graduated chemical engineering a couple of years ago from UNSW. So I was exactly where you guys are right now a few years ago. Following that, last year, I started my PhD, again, in the Particles and Catalysis Research Group. I researched materials that are used for energy conversion reactions. So this is mainly graphene or carbon-based materials, which are used to, for example, produce hydrogen from water or convert waste CO2 into things like methane, methanol, and useful products there. More recently, we found an opportunity where we started our spin-off company, Switch to Engineering, which is spinning off or translating some of the research that we're doing in the lab on a very fundamental level into an actual application. And yeah, we were very lucky to win the Peter Farrell Cup and also be funded by Atlassian with their family fund to push forward with our technology. And also very recently, I was elected to the University Council, which is sort of me exercising my enjoyance for policy and strategy around teaching, learning, and research environments for the university and making sure that we can make the best impact possible. So I'm not really sure about you guys, and I've been to quite a few seminars now, but one of the things that I keep getting is sort of a feeling of intimidation, and I'm a little bit daunted because sometimes you have some really, really, really amazing speakers, whether you're speaking or you're an audience member, and they're really high achievers in the chemical engineering field, and sometimes you feel a little bit like an imposter. And I just want to highlight that, you know, at the end of the day, everyone is sort of in the same boat. Everyone has their own weaknesses. Everyone's human. And it's really about playing with your strengths, acknowledging your weaknesses, and just being yourself and being who you are. So I think that, you know, over the last couple of years, something that I've learned is to just really be calm and confident and be yourself, and you'll be fine at the end of it. And the mantra goes sort of fake it till you make it. And I used to sort of believe that, and I used to think that that used to be something that you needed to do to fit in. But as I sort of have grown personally and professionally, I realized that just being yourself is key, and acknowledging and being able to laugh at yourself is something that's really important. So if you ever feel out of place, don't. Everyone's really on the same boat as you. And so I want to talk a little bit about Power-to-X, and Rose introduced this really well earlier, so I won't add too much detail to that here, but this is sort of what chemical engineers' fantasy is in terms of how we can integrate renewable energy generation into viable chemical processes. So right now, Australia is one of the world leaders in terms of solar cell development. We can make really, really efficient, cheap solar cells that produce really cheap electrons, and you can get these electrons for less than 3 cents per kilowatt hour nowadays. And so if we want to really integrate renewable energy into industry, we need to make sure that we have the processes that are available for that. So not everything can be electrified, right? So, for example, we can take those electrons from the renewable energy generation. We can pass them through a water electrolyzer to produce hydrogen. We can pass them through a nitrogen electrolyzer to produce ammonia or fertilizer, as Rose talked about before. Or we can even use waste CO2. And with those electrons that we get from the renewable energy generation, create things like methane, methanol, formic acid. And all of these things are really important energy carriers and fuels and chemical feedstocks that we can use in industry. So by using this sort of P2X pathway, we're really coupling the end need, which is sort of, for example, a chemical feedstock, which can be used to synthesize other chemicals, or it can be used as a fuel directly. And we're coupling that with the really cheap electrons that we can get from the renewable energy side of things there. And so obviously, for this to work, and as Professor Lewis was talking about before, we really do need the economics to match up. So, for example, if I'm buying electricity at 3 cents a kilowatt hour, which is extremely cheap, I need to make sure that the end product of whatever I have is worth more than equivalent to 3 cents a kilowatt hour of electricity going in. So for that, we really need to maximize the use cases of these end chemicals. And I'll be focusing a little bit on hydrogen here. And I find hydrogen really interesting because it's sort of the cornerstone of the whole P2X concept, where hydrogen can be used as a chemical feedstock to make other things like fertilizer, methanol, urea. You can use it to heat things up directly for industrial processes or even domestic heating. And you can use it as a fuel as well. So it's a great replacement for diesel once we have the infrastructure up for it. And you can even use it or they're trialing applications in aviation. And so what that really means is that the economics of that P2X pathway doesn't really fall down to just hydrogen as a commodity on the commodity market, because that would be worth very low amounts, but rather what hydrogen can be used for. So for example, if it's replacing diesel and it's cheaper than diesel, the cost is not so much how much you can sell hydrogen for, but it's how much money you save by using hydrogen as opposed to diesel, which is quite expensive, as Professor Lewis was talking about before. And the other thing that we need to sort of establish to make sure this Power-to-X pathway really works is that when we're making the hydrogen, we can really minimize the cost in that process on itself, that electrolyzer component there. And this is like a very simplified example of that here, where you can split water using those renewable electrons here that you get from the generation sources. And so what you'll find is that there are two main factors that really define how much hydrogen is going to cost you to make. And that's firstly, the average price of electricity, which, as I mentioned, because we have so much solar capabilities and we really are driving the cost of electricity down, we'll leave that to the PV guys to sort out. But the other thing that we can sort of make or have control over to make this process cheaper is by reducing the amount of electricity required per kilogram of hydrogen. So at the moment, industrially, I think it's about 55 or 50 kilowatt hours required per kilogram of hydrogen. But if we can drive that down even to 45 kilowatt hours per kilogram of hydrogen, we can really reduce the cost of hydrogen to about $2 per kilogram, which is what the National Hydrogen Strategy really wants us to aim towards. So in order for us to really realize a P2X as a real possibility, we need to A, make sure that we're using the right hydrogen in the right use cases and application, and B, that we can minimize the cost of hydrogen production. And this is where Switch 2 comes in. I might add that during our final year design project, when I was an undergraduate chemical engineer, we were required to optimize both the carbon footprint and the cost of a very large brewery operation. And that inspired us to sort of dig a little bit further and think about what the challenges of a brewery actually face are. And, you know, the first one is that they require so much energy, about 40 kilowatt hours just per 100 liters of beer. And that's equivalent to about 75 kilograms of carbon dioxide released per hectoliter of beer. And when you start thinking about the distribution chains of a brewery and also how much wastewater, it's about 5-to-1 wastewater produced per liter of beer produced. And that's all really rich organic, highly concentrated organic waste that has really high entropy behind it. You can start to see a problem there. And so the opportunity came for us when we realized that most of the energy demands for a brewery are actually satisfied currently by natural gas and LPGs. These are liquid and gas energy carriers. When the brewery operates at nighttime, when they don't have access to solar energy, whether that's on-site or they're buying it directly from a solar farm, they revert back to grid energy. And at the same time, they produce copious amounts of wastewater, again, about 5-to-1. So if a brewery produces 1 million liters of beer, they have about 5 million liters of really really organic, rich, high enthalpy wastewater that's not being used. And so when we started to think a little bit back towards how we can really optimize how hydrogen is used and what we can actually use to make hydrogen, the brewery really clicked for us, because you see the two on the left here are things that hydrogen can actively replace, while the thing on the right here is what we can actually use to make hydrogen. And that's really where Switch 2 came alive. And we designed a concept for a wastewater electrolyzer. So instead of splitting water, which is what traditional electrolyzers use, we designed specific catalysts in the Particles and Catalysis Research Group so that we can actually oxidize the organics in the wastewater of a brewery. And what we're finding here is that thermodynamically, it's actually much easier to split these organics up as opposed to splitting water. So by actually using wastewater as a feedstock for the electrolysis process to produce hydrogen, you can actually reduce the overall energy requirement by up to 30% compared to the state of the art. At the same time, typically hydrogen, which is produced at scale, requires a wastewater treatment plant to purify the water before it goes into the electrolyzer. But now we're designing catalysts that are robust to a lot of these impurities that are found in brewery waste so that they don't foul the catalyst, and we don't need that really high purity water coming into the electrolyzer. So it means that we can decentralize hydrogen production by using these waste feedstocks. And as Rose was talking about earlier, pure water is really a scarcity in Australia. So by using this waste, which is otherwise not really utilized to its full extent, we can produce that hydrogen. And a really great thing about that is because it's really difficult to actually electrify a lot of the brewery's energy requirements. So an obvious question is, well, why don't you just take the solar energy and can use that directly into the brewery? But it's not actually possible because of the industrial heating requirements for the transportation, for example, or even just for heating up the boilers to get the water out of the brewing process. This requires really a liquid or gas energy carrier that can be combusted. So hydrogen really fits the bill there. And it means that we can actually now take that renewable energy, convert it into hydrogen, and apply it into a brewery. Obviously, by avoiding the use of LPG and natural gas, we can reduce the carbon footprint of the brewery. And at the same time, because we're not relying on external forces and we don't need to buy those energy carriers, we can actually reduce the operating costs for the breweries. And so the idea of Switch 2 is really to sort of identify that specific use case of where hydrogen can be used, a brewery, integrate that smoothly into the actual brewery, because that systems integration step is a really big barrier towards hydrogen's implementation, and also reduce the cost of hydrogen production by developing and translating the catalysts that we make in the lab that work good for wastewater degradation and applying that into an actual application there. And so when we're currently working on a feasibility study with one of the larger breweries in Australia, and for a brewery that produces more than 150 million litres of beer every year, you can really see some substantial cost savings and CO2 offset. And at the same time, they become market leaders in actually becoming more of a sustainable FMCG economy and really appealing to the purpose-driven customers as well. And so in terms of where we've taken the startup, so last year we sort of came up with the idea, we did some tests, we ran some simulated brewery wastewater in the lab. We were lucky enough to win the Peter Farrell Cup from UNSW, and then that's when we were shortly funded by the StartMate Accelerator Program, which is a venture fund backed by the Atlassian Family Fund to actually progress our technology further. We've tried real brewery waste, and we've scaled up about 200 times. So now we can actually process about 20 kilograms of hydrogen per year in our system. At the same time, we spent quite a lot of time making sure that we had a really robust product market fit, because at the end of the day, breweries aren't interested in hydrogen. They're interested in brewing beer, right? So we had to make sure that we came up with sort of modular autonomous designs that are able to fit in with the current brewing culture and the current brewing practice in the industry as well. And so we're currently working with some of the major breweries to look at a pilot scale implementation next year or the year after, depending on how nice or mean COVID is to us. That'll be producing about a ton of hydrogen per year. And we're also lucky to secure some university and government grants also to fund our progress so far. And so I just want to acknowledge this all really came from our work, obviously, in the Particles and Catalysis Research Group, where we were able to actually take ideas from the lab and really be supported by Rose to push that out there and actually make solutions out of it as well. And I want to also acknowledge my two other co-founders, Bajil and Kushal. And I really want to impart to you guys that doing a PhD in research isn't just all about lab work and writing thesis, It's really about the professional development of yourself, the leadership, the innovation, the entrepreneurship that you gain throughout your PhD studies, and all the people that you meet along the way. It's really just that journey of taking a technology and applying it to where it actually matters. And so when Rose was talking about a bit before, I think she called herself the past. I don't think she's the past. I think she's definitely today, but she's really given us the opportunities, and people like Professor Lewis as well, to really take the reins and go out there and make some change as well. And with that, thank you very much. And I think I'll end it there.
Thank you for that, Constantine. That was a lovely presentation. Our next speaker will be Paul Downher. He is a professor at the University of Minnesota. He was the winner of the 2019 ACS Sustainable Chemistry and Engineering Lectureship Awards for his contributions to green chemistry. He won the American Institute of Chemical Engineers Catalysis and Reaction Engineering Young Investigator Award in 2018, and he'll be speaking to us today about alternative energy and electricity production.
Thank you for the invitation to present to the IChemE Student Summit. I'm Paul Downher. I'm a professor from the University of Minnesota Department of Chemical Engineering and Material Science, and I'm going to be talking about using biomass and sustainable feedstocks to make new chemicals and materials. If we think about the status quo for chemicals and materials in general, right now we take upstream fossil fuels and we make a slate of chemicals, including ethylene, propylene, benzene, butadiene. We turn those into plastics, and then those go into products. Of course, these products are life-changing and great for the economy, but the problem is they're end of life. What do we do with them when they're done? And of course, the other problem is, what do we do in terms of feedstock into the future? What we would like to do is find things that are more renewable, that won't have long-term feedstock shortages, and something that we can use that can be reprocessed, used again and again in a sustainable way. Now, one approach to this is to take a completely different feedstock. We could take things like trees and grasses, non-food biomass, and from that make the same chemicals we already get from petroleum and natural gas, things like ethylene, propylene, and benzene. Then make the same plastics we already have, make those into the products that we use right now, like bottles, shoes, shirts, cars, food packaging, all the things we do. But then also find a way to unmake them, so convert them back to their plastic polymer, or convert them back to the chemicals and use these in a closed loop. So once we've made it, we unmake it, and then we use it again and again and again in a sustainable carbon cycle. Now, how do we do this? Well, ultimately, what we need to do is we need to start from something that comes from biomass. And the molecule of interest here is glucose. You can see it there in green. And we can make glucose from a lot of different renewable resources for as low as 10 cents per pound of carbon. You can see there on the scale on the left. Now, the things we're trying to make are also very low cost. So molecules, like you see there in red, is paraxylene. That's the key ingredient in things like plastic bottles or polyester shirts or car parts. Those also sell for under $1 per pound of carbon. These are US dollars. Now, ultimately, what we want to do is we want to find a way to go from the green glucose molecule to the red paraxylene molecule. And there are many different chemical paths we can use to do this. Some have more steps, some have fewer steps, but each step in the path adds cost. And so we need to find the sequence of steps that let us get between these two chemicals in a way that's lowest cost and come under the sale price, so at the end of the day when we sell it, we can still make money, and it'll become a viable, sustainable process. Now, how to do that? That's the chemical engineering process challenge. Well, we need new chemistry. So if we start in the top left there with glucose, that's the molecule we get from biomass, and we dehydrate that, we remove some of the water, it'll make these pentagonal molecules you see right here. The second molecule from the left is called hydroxymethylfurfural. Then we can take off some of those oxygens by hydrogenation. And in that last step there in yellow, we can convert the 5-atom ring, the pentagon, to a hexagon, just like we would get from petroleum. And so we put a lot of focus in the past 10 years into that reaction right there. How do we take the things that biomass makes and natural sugars and make the things that come from petroleum that we already use? And so in the past 10 years, we've done this, we've focused on catalysts that can do this chemistry effectively. You can see on the left here in pink, this is the performance of the catalyst from when we started in 2011 the HY catalyst was only a little bit below 40% selective, to catalysts now that are 97% selective. They're almost perfect. And that's taken this technology from something way too expensive to something that's now commercially viable. Now, how do we do this? We track the price of the materials that we can make renewably based on the performance of new technologies. And one of the new technologies we've invented for this is a new catalyst we call PZacyl. So P is for phosphorus, and Zacyls are zeolites, if you're familiar with that material. They're a silica that has these tiny little molecular sized pores. And you can see in the pictures there, they actually have unique shapes. And then within each of those shapes, each of those has an atomic structure that lets molecules go in and out where they can react. Now, starting from 2013, we've taken based on improved performance and taken the price at which we can make renewable molecules like this from prices that are way above the price of conventional fossil fuel derived molecules all the way to prices that are below $1,000 per metric ton, and now they're economically viable. Now, that's the technology we started with. We've also looked at other technologies, including renewable rubber. For renewable rubber, we need the molecule you see there on the far right called isoprene. It's 5 carbons, has 2 carbon-carbon double bonds. And again, we're going to start with glucose because that's what we can make from biomass. We'll take that, we'll use fermentation to make the second molecule you see on the right, diacid. We'll use metal catalysts to convert that to a 5-atom ring again. And then the final step, we'll dehydrate that and ring open it to make isoprene. Now, we've developed that technology in terms of the chemistry, but then we also need to develop a process technology. So we'll take those reactions, we'll convert them in using a computer simulation, in this case, design reactors and separators and process sequences. And then we'll optimize that to reduce the cost for both the capital cost to buy all the equipment to install it, but also to operate it. You can see here all the different parts of the chemistry show up in different colors and contribute to the cost in different ways. Now, ultimately, we can take that design and say, what's the cost of everything, and how does that add up over time compared to conventional prices? So here's where we started 3 years ago in there in the pink. And you can see that the prices, if you look at it, the price of isoprene we could make with that process is approaching the commercial prices, but it's still too high. And so we pick out and say, what catalyst can we make that could drive this price down to be competitive with isoprene prices from India and the USA? And isoprene is very interesting because it's one of the key components in renewable car tires. So we can make renewable isoprene from biomass, then we can make renewable car tires around the world and all sorts of other renewable rubber applications. Now, this brings up an interesting point of what we're trying to do. We can take biomass and we can make the molecules we already use. So things like paraxylene and isoprene you see there on the right. If we make those exact same molecules from biomass, we can put them right into the commercial processes right now and make cars and tires like we already have. And that's great because those technologies are already mature, they already are very useful for society. But biomass means we can also make new molecules, such as the molecules you see on the left there, that create new materials, that do things we can't do with conventional fossil fuel-derived chemicals. And I'm going to give you an example of one of those that you see there on the bottom left. That's a molecule called oleofuran sulfonate. It's a class of molecules we've invented that compete for cleaning laundry in a way that's much better than the conventional laundry detergents you can buy off the shelf. So let me give you an example here. Here's a bottle of laundry detergent. And into that, you have all sorts of things. It's a formulated product, which means it's made of many things, many different chemicals and different things. So roughly a third of the bottle that you buy is water. So you're buying a lot of weight there in the water. The blue that you see there is called the surfactant, stands for surface active agent. And that's what does a lot of the cleaning. Not all the cleaning, but a lot of it. And it forms micelles that can strip oils out of your clothes and solubilize it in water and remove it, clean it. Now, the problem with this molecule you see here in blue, the LAS, or linear alkyl benzene sulfonate, is that it's not stable in a lot of conditions. So we add in all sorts of other chemicals called chelating agents that grab all the metal ions and let the surfactant work. We're going to propose a new class of molecules here in red that do everything that the blue and the green do at lower concentrations and better performance that are made from biomass. So here's these molecules. They come in several tunable structures. And the problem is that with conventional surfactants, they're not stable. So what you're seeing here on the right is The conventional surfactant, like you get in the off-the-shelf laundry detergent, is called LAS. And the new biomass-derived molecules are called OFS. You can see here, I'm showing their stability based on their clarity. So you can see on the right here, there's a file. And behind that, you can see our University of Minnesota logo. Now, as I add in more and more calcium, like you would have in hard water, the conventional LAS laundry detergent starts to get opaque. You can't see through it because the surfactant forms a crystal, it stops working. But the oleofuran sulfonates stay crystal clear, even up to 10,000 ppm calcium. It's an enormously high amount of calcium. Now, what you can do with these new molecules can't be done with conventional surfactants. You can make all these different types of products, paints, inks, and coatings. You can make detergents, personal care and cosmetics, agrochemicals, and use them for all sorts of applications, oil recovery. But because they're so stable and so effective as surfactants, you can make formulations that are cheaper, more sustainable, and in new applications that you couldn't possibly before. So because this technology was so exciting, my student and I that helped invent this formed a startup company called Ceronics Renewables. You can read about them online, and they market these bio-derived molecules as the EO6 surfactant. So ultimately, what's great about biomass chemicals is they have a bright, sustainable future that continues to grow every single year. We already know that we have the ability to remake all the chemicals from the fossil fuel-derived industry in the next 2 decades. The chemistry is there. And what's happening now is that the economics are getting better every single year to the point where we'll be able to compete without any sort of subsidy with fossil fuel-derived chemicals. We also know that new chemicals can outperform existing fossil fuel-derived chemicals. And in this case, because I'm from the University of Minnesota, we study this because at Minnesota we have all sorts of forestry products and agricultural products that let us be a leader in sustainable materials. But of course, places around the world can compete just as readily as Minnesota. And these technologies, there's nothing special about Minnesota. They can be used in every continent around the world. So let me just thank a few people. We do our work with the National Science Foundation for the Center for Sustainable Polymers, but also we do have a catalysis focus that's funded by the U.S. Department of Energy and our local farmers. So thank you for your time, and I appreciate you listening.
So we'll jump straight to the panel. So we'll invite Constantine, Rose, and David back so we can get started with some questions. So we'll currently go ahead with the questions that we have ready that are published in the Q&A section. The first one here, just slowly waiting, David's back here as well, great. So the first one here is there anything majorly holding back advancement in renewable energies? What are those factors? Does politics play a major role? Rose, maybe you'd like to start?
Okay. Yes, I think politics definitely is one of the things, and I see that in terms of the renewable and fossil fuel, it doesn't have to be one camp, versus the other. I see that if we can work together, that will be the one that I think will be able to drive the solution. Because there's a lot of opportunities. So that's one of the things that we're talking about when we're talking about closing the carbon loop, is looking into how to use the renewable energy in order to convert back the CO2 sustainably. Because we still require those hydrocarbon for a lot of the things we need as a sort of a human. We need it for chemical, for plastics and stuff like that as well. So I think that the holding back, I know that people's talking about the cost, but I think it's more like I would say that if government could have a policy to encourage more collaborations, I would see this probably accelerate much faster.
Anything to add, guys?
I just want to echo what Rose said. It's policy helps a lot. So when you work with business, if there's the right policies in place, it gives their investors more comfort to take more risk. And I think renewables are risky because of the economics. But I think if we got the right government policies, then our investors will be more liable to take those risks and invest in these emerging technologies.
Yeah, I would agree completely with what was said. And I think from my perspective and my point of view, being involved a little bit with the whole venture cap space and startup space as well, is that there really needs to be a strong synergy between, for example, a startup, the venture cap, the government, and a research organization like a university. And I think sort of getting out a good framework where those four entities can work in tandem is really, I guess, encouraging to push and translate that technology that we're making in the lab into application. And I think in Australia, we're very lucky in terms of our inputs into research are really well developed, and a lot of the time the government really does support us through that. I think it's just really getting it out of the lab and actually tailoring that technology into a solution that we can work on. And I think the New South Wales government is really working on that recently, with a lot of focus being on that translational research as well.
Great. This is another question for Constantine, building on your entrepreneurship. How did you balance education and its challenges with entrepreneurship? How did you go about converting a degree and your knowledge into a startup and business in the industry?
Yeah, that's a really good question. I think it's quite difficult, and I might preface and say that I haven't been able to really commit 100% of my time into the business. So the PhD has really been my first priority there, and it was really a challenge of trying to tailor what I was doing into the lab with that end sort of application in mind. And I think the main challenge there with doing that is that sometimes you have to work with different caps on. So one day I'll have my lab cap on and I'll be looking into really complex spectroscopic data. And the other day I'll be trying to sell my idea to a VC or a customer or someone in the general public. So it's really about getting used to sort of those different transitions and being able to develop skills in different area. And I think that when it does sort of come, it comes naturally. So it's not really a point where I'm sort of like, okay, today I'm going to start a new business and do this new idea and spend 50% of my time doing this. It's something that sort of builds up over time. So I had my research going, and once that was sort of comfortable and I could sort of manage my time there, I started looking slowly into other areas. And I was lucky enough to have, and I keep emphasizing, it's a very supportive group and supervisor who really gave me the opportunity to be sort of investigative in those areas. And I was just very lucky that it did pay off at the end there. But I think the key is sort of just really developing skills in different areas and sort of putting yourself where luck can find you. I think that saying has really been prominent to me being able to do these things.
You mentioned also the Peter Farrell Cup and through the university, the support you got there. Do you think that really made the startup and the business a reality?
Yeah, I think it was very exciting because the Peter Farrell Cup was sort of our first big win. I think more than anything, it just gave us the confidence to do things and push things forward there. The universities are generally, or UNSW is like, I'm not too familiar with other universities, but UNSW has a very, very strong entrepreneurial program where they really do give you the support and the exposure to venture caps, to business, to people from industry who are interested in, for example, your research or your idea. And so Peter Farrell Cup was sort of one pathway through that there. And I mentioned at the beginning of my talk, at the end of the day, you just want to be yourself and be confident. So although the Peter Farrell Cup really did open my eyes at the time, looking back at it, even if I hadn't won the Peter Farrell Cup, at the end of the day, I would still have the same sort of supports, the same sort of technology, and the same sort of, industry reach in that sense there. So it did, but it didn't have to.
David, you also mentioned your aptly nicknamed Waste to X. Did you have anything to add regarding that?
Sorry, what was the question?
So with regard to managing research and also the startup and industry, how to combine them and converting them together and using your knowledge with both.
Yeah, look, it's challenging. I encourage everybody to do a startup because you learn so much about business. You learn a different way of communicating. But it's very challenging to do both research and run a small company. I personally started I went 50% academic and 50% into the company, then 100% into the company. But you do learn so much. I think University of Adelaide, like UNSW, has put in more focus nowadays on developing entrepreneurial skills in students and giving them the opportunities to do startups, to explore new ideas, different prizes, some seed funds, etc. And if we look at the US, they do it really well. We're a little bit behind the eight ball compared to those guys, but there's nothing stopping us. And I think in our curriculum, we should be teaching more around business, to our chemical engineers. We've got the core, and we need to really explore the entrepreneurial side of being an engineer.
Yeah, I'm taking a course like that at the moment, and I found it really valuable. Next question here. How will these new processes be integrated into industry? Is there a lot of resistance to change due to pre-existing investment in conventional plants?
From my perspective, industry are always looking for innovation. It's boring, but making things more efficient, i.e. save or spend less money. So industry are quite willing to try new things, but their risk appetite is quite variable. So obviously they've got their processes that make a profit, and it's very difficult for them to take too much risk that might reduce their outputs, for example. But I think industry are a lot more accessible than we give them credit for. And once again, with students, we need to teach better communication skills and academics on how to talk with industry and understand their needs.
Yeah, I'll just add more on that. I think that it also depends on the industries as well. Some industries are more ready in terms of capturing or embrace new technologies. But I think that in Australia, we need to do that in order to be able to be competitive, especially in terms of our manufacturing and chemical industry, which is, for me, I see the last sort of 30 years since I graduated is actually diminishing. But I think that it will come back, and with the support from the government, I think in order to be able to compete with other countries, it's not just US, but also China, India, we have to be innovative. And having those entrepreneurships, innovations, things that embedded into our curriculum, I think that will be good, so that our graduates, in order to be able to really looking at creating new industry, creating new technology, not just have to work with industry, but create their own industry.
Yeah. Professor Rose, another question for you. Is it feasible to operate the integrated solar electrolyzer and thermal catalysis process at an industrial scale? If not, what are the major problems faced in doing so?
I think so. I think it can be integrated in terms of the electrolyzers, because in fact that there is a small demonstration plant already that was supported by industry and ARENA. ARENA is the Renewable Energy Agency. So looking into using the concept that I showed before, using the solar panel to convert water to hydrogen and use the hydrogens then with the CO2, but not sort of the designs like what we had that. What we had that is more for a demonstration for high school students. Is sort of easy, but it's possible because, and I think that always that when you harness the sun energy, because the sun, when I show it, the spectra it's a white spectra. We harness the light, but we forget about the heat. If we can harness the whole things, it should be able to make the process more efficient. And there are quite a number of processes as well. Even the Haber-Bosch process, there's already again a demonstration unit in UK looking at capturing the heat of it in order to power some of the thermal catalysis part of it. So I think that's probably chemical engineers the best profession or discipline in order to be able to deliver that, because we know the process and so we should work with other engineers like mechanical engineers, which is on the thermal part or some of the heat exchangers part, but we should be able to really deliver that in the future. I'm hopeful.
There was another question building of what you just mentioned. If someone from a mechanical engineering background that's interested in hydrogen production or similar technologies, want to continue into chemical engineering in a master's, how difficult do you think that would be, and what challenges do you think they would face?
We actually have already a success story. One of our PhD students who is now a postdoc fellow and working very, very well and actually helping me to get these training centers that was announced yesterday. He's a mechanical engineer from Hong Kong before. And initially that it was a bit of a struggle for him to learn the chemical process. But then I think that a lot of the times that, when you do a particular degree, you are given the skills to be able to learn. You might not get all the knowledge, but then you have that skill to be able to learn. And during your PhD, because he's straight doing PhD from mechanical engineer, he's able to learn. It's maybe the first 6 months, it's a bit struggling in terms of the chemistry, but he also learned chemistry from high school. So it's not too difficult as long as you have the will and ability to learn new knowledge.
Great. We'll move on then to the next question from Ingrid. Will a policy change such as a carbon tax make biofuel options more economically viable? And do you think these will need to be a policy intervention to allow sustainable energies to flourish?
I think the answer to that is yes. I was so happy when we had a carbon tax on the horizon and then it stopped. But that's a great way to encourage industry to follow certain pathways. I think the debate's well and truly dead around climate change and carbon, etc. And now we just need to work out how we're going to monetize carbon.
Yeah. Next question is for Constantine from Joshua. What happens to partially oxidized wastewater after electrolysis?
Yeah, that's a very good question. So we're trying to exactly identify what's going on in the system at the moment. I think one of the challenges of sort of working with less defined systems where you can't control the parameters just as well is that it's sort of quite difficult to probe actually what's going on there. So we know that by using different catalysts and different sort of applied potentials of voltages in oxidizing the waste, we can control how much that waste is actually oxidized. So if we apply very high potentials, typically on some transition metal catalysts, for example, we can get quite a lot of carbon dioxide production. So the goal here is to operate at lower voltages so that we can avoid carbon dioxide formation. But at the same time, not completely, disrupt and disorder the waste treatment processes, because breweries already have existing wastewater treatment plants. And indeed, the large breweries, and the one that we're working with particularly, produces biogas from their waste organics. And so we still need to maintain most of the carbon content in the waste so that it does get further processed in the wastewater treatment plant. But we just want to avoid the carbon dioxide production step there. And as far as to my knowledge goes, and this is something we're still really trying to nail down when we look at more sort of industrially related trials, is that it doesn't necessarily affect the biogas production downstream, because some of the chemicals and the organics that the bugs decompose in the organics to produce that biogas aren't the same ones that we're oxidizing.
Yeah. Thank you. Another question for Constantine again. How important do you think learning coding is for chemical engineering students from the start? Specifically, non-traditional programs like C++, Python, that may not necessarily be taught within the curriculum.
Yeah, that's a really good question. I think I am rubbish at coding, and I think I had that on my slide before. It's just my brain doesn't work in that way, and I'm completely okay with that, and I accept it. So I can work on it because I acknowledge that. I think it's quite important. You don't need it for most streams of chemical engineering, especially in a lot of the material design streams, but it can really make your life easier. It can open more doors in terms of understanding new areas of research that are around, for example, machine learning and AI. You can process data a lot quicker if you do have some basic knowledge. So I would suggest that it's good to have a fundamental understanding and sort of an appetite to know what the code can do, And depending on what pathway you decide to choose, sort of depends on how many different languages, how in depth you really want to learn the code. So it can help. Basic knowledge does really support that, but it's not necessary to do well, I think.
Yesterday, someone from the metallurgy stream indicated that while you don't pick it up necessarily at university, throughout industry and as you start working, if you go into a tech-related industry, you do pick up those skills. Is that something you would agree with?
Yeah, 100%. I think that a lot of the stuff that I do as part of my PhD is really testing new orders and really sort of pushing yourself further to learn new things. So it really changes from, for example, an undergraduate research project where someone's just telling you to do things in the lab and you're just doing it in the lab for the sake of doing it. It really gives you the opportunity to learn new things and push yourself further. So again, if I didn't pick up any of it during my undergraduate degree, and I'm slowly practicing now. So it's something that you can build up yourself. And I think the other sort of set part of that is that a lot of the time the coding that you'll learn is really specific to the application, like you were mentioning about on-job skills and skills that you learn specific to an application of coding. And so, that sort of area there may or may not be as complex as sort of learning the real fundamentals on a sort of like a computer scientist level as well. So you might only need to learn what you need to know as well.
Great. So this is for everyone. How do you think students wanting to do research or explore fields such as alternative energies, etc., should immerse themselves in such endeavors outside or within their chemical engineering curriculum?
Okay, let me try. So okay, I'm not sure.
Maybe we can
immerse themselves in research.
I think yes, that's probably the main question there.
Okay, so I'm guessing most of our Chem curriculum around the country is similar, where in the final years of their program, they have the opportunity to do research. And I encourage all the students to get to know what faculty members, what their research expertise is, what areas they are interested in, and just start talking to the professors and postdocs and PhD students about what's going on. And I'm sure 99.9% of research groups would open their arms widely to encourage undergrads to get involved with their particular projects. I would encourage people to do PhDs. I think industry is more and more valuing the skills that a student gets when they do a PhD. It's high-level skills and very useful, not just in research, but in industry per se.
Yeah, I think I was not really clear about your questions, but if I got it right, is that I think the students need to have sort of the passions as well of what they want to do. If they want to do the alternative energies, why is that? They need to sort of look for it. And normally I encourage undergraduate students to explore, to find out more information, what they wanted to do. And doing PhD project, it's again what Constantine sort of say, you acquiring skills. So if you're working in a project that is on energy, it doesn't mean that, if you found that is not really your calling later on, it doesn't mean that you fail, because all those skills that you get can be transferred to a lot of things. And I mentioned earlier that my earlier project was on environment, but a lot of the science and the engineering principles can be actually translated to different applications. So I think you need to find your passion if you want to do research, whether it's alternative energies or anything, and speak to people and speak to academics, as what David sort of mentioned, ask and talk and explore. I think that's very important.
Yeah, and engaging in like webinars like these, you can find them on the internet with a quick Google. I think is a really good way to get involved as well. Were there any websites in particular that you knew had good resources? Anyone?
Website on alternative energies, or is website
for alternative energies in particular?
Google Scholar.
Google
I
Scholar.
DOE, the Department of Energies, I normally like to go there because they normally have a very nice good reports of the latest developments and things like that. and they sometimes have videos links as well. And sometimes you just Google, a particular topic. Say, for example, I'm interested in direct air captures, which is capturing CO2 as the latest technologies. Just Google that particular topic, and then you will see a lot of webinar or YouTubes available as well.
Yeah, I think a really good place to start, if you're sort of getting into it, is having a look at what we're doing in Australia, particularly, for example, with the National Hydrogen Strategy, or even being from New South Wales, what they're doing in New South Wales in terms of what projects are sort of getting underway, and just sort of wrapping your head up where we are at as a country in terms of that landscape. I think in regards to the previous question, I started in the lab at the end of my second year doing what was called a Taste of Research placement in the same research group that I'm still in at now. And so what I find is that it's never too early to sort of get involved and just have a conversation with someone. It doesn't have to be with the group leader, but maybe even other PhD students. And people are usually very happy to talk about what research they're doing and sort of how you can get involved as well. So I think don't be shy is probably my piece of advice there. And when I was an undergraduate student, I was heavily involved with the IChemE student chapter called the JSEC, the Joint Chemical Engineering Committee, which was we had I guess seminars like this between IChemE members and Engineers Australia. And I believe they're still doing it now. So even after this student summit, please do keep getting involved. The face-to-face seminars will probably resume next year, I hope. And so they're really, really good opportunities to build that professional network, to build that professional skills, and just sort of get immersed with other people who are doing things that you want to do.
Great. Next question. What is the job prospect for alternative energies in Australia compared with other industries? It's a pretty ambitious question.
I really hopeful, and I think that as far as I know that a lot of the job now need to be looking at sustainability, a lot of industry. So you might not sort of working in industry sort of calling them as a renewable energies, but a lot of industry now they have to think about that. Say for example, even say Rio Tinto or BlueScope Steel, all of them they're looking into using renewable energy. So looking at, for example, hydrogen in their processing, for example, and how to use more of the renewable energy in terms of their processing. So those kind of things that I think that is not really calling a renewable energy industry, but it will be embedded in many manufacturing and chemical industry. So doing a research or project into that I think that will be benefit, because you have a lot of avenues to go into.
Great.
Yep. Can I add to that?
Of course, go for it.
So I think students, when they graduate, they're all chemical engineers, and you need to have something what differentiates individuals. So if a student has done extra research, for example, in alternate energies or sustainability, that's going to make them a little bit different from the other students. So they got something additional to offer industry. And industry are looking for new ideas and innovation. So the job prospects are good if you've got something new and novel to offer.
This is another question for you, Professor Lewis. What are the steps being taken to overcome the challenges you have mentioned regarding HTL? Okay,
so I mentioned we've been funded by ARENA to build our commercial demonstration plant. So Southern Oil have done the front-end design on that. The plant is going to be built in Ipswich, in Brisbane. And basically, we need to build it, commission, and operate. So United Utilities and Melbourne Water are engaged in that project. The challenge is, as it gets closer to commercial scale and operation, the economics become more and more important. The biggest challenge for us is to find additional value from the HTL products. So we're very competent and comfortable. We can operate the technology. We can produce a refinable crude oil, but we need to find other value in the reactor products. That's the big challenge now.
This question also asks, could you share your opinion on whether this process can be applied to countries other than Australia that may be less developed?
Yes. So we are definitely travelled before COVID, exploring opportunities in other countries. And we've deliberately tried to make the technology as simple as possible. So imagine a rice cooker. It's probably not much more complicated than a rice cooker now. It's really simple. So it could be adopted in other less developed areas, but you do need energy to operate it. So you need an energy source to be able to operate HDL, whether that's gas or electricity.
Another question here that I've just been sent in chat, as the Q&A function isn't working for them. This person just wants to know how they can implement these research topics into commercial jobs. Is it more specifics, do you think, or is it just understanding the struggles in industry?
Research talks, did you mention?
Yeah. So like in these specific like research topics, they want to know how they can implement these things, or I guess ideas and that you have brought up. And yeah, I'm not too sure.
Yeah, I'm not sure what I'm very clear with the questions, but how do you use the research topic that you're doing in terms of convert it to commercial job? Is that what it means?
Yeah.
Is that what the question is?
We'll take it like that, yeah.
Yeah, so I think that all the research in chemical engineering and within a lot of other fields is that there is always a focus of what it's going to be applied for. Say, for example, when we're talking about the work that we're doing in terms of Constantine work, which is converting waste using electricity into hydrogens and those kind of things. So, and when we do the research, we probably focus on a certain things. We're trying to develop a best catalyst, for example, a platinum or single atom platinum, and we're trying to understand the science. But then from that, then we have to also come up with the questions: is what is the things, what is the applications we want, and then from that we can have to looking into to design the system. So it's not just whatever we do in the lab, but how we're going to be able to implement that. So I guess that a lot of the research, we always have that goal in mind in our, so as a final aim that we will have to deliver in terms of, okay, we wanted to make hydrogen as costly as possible and as efficient as possible. In that way, then you can really translate what you do in the lab into the commercial benefits. I'm not sure whether that is the question, but if you're talking about a research topic in order to convert it to commercial, that means that you have to have a goal in terms of focus on that in order to translate that.
Yeah, I agree. And I think, like Rose said, the value chain of alternative energies or power to X or hydrogen or whatever is really large. So you not only have to know about sort of the raw materials, how to actually make the hydrogen, how to transport it, how to store it, how to actually use it. And so I think, you know, seminars like this or other seminars that are specialized around alternative energies really do focus on different points, and understanding what the pain point is of each sort of section in that process is really important to sort of getting your breadth of understanding of what's actually going on in industry. And so whether that's translating technology, whether that's applying for jobs, whether that's sort of having an industrially focused research thesis in your final year or anything like that, I think having a really good understanding of, in general, what people are doing and how they're doing it and where they're doing it and where on the value chain they lie, it really does sort of allow you to make the most out of whatever you're trying to achieve there. Again, as I mentioned, whether it's just applying for jobs or a thesis, for example.
Just one more thing to add up, and also connecting to industry. I think talk to them, because a lot of the works that we're doing, although it might not be supported by industry, but we do talk to some of those industry and telling them or giving organize some sort of seminar and by brainstorming, then you will come up with ideas of how to actually translate that, whatever you do in the lab to the commercial sort of process as well. There's quite a number of projects that we have, which is initially we never thought of that but by really having sort of talked to people in the industry, and it's actually spin it, from something that we sort of thought that it maybe it's just a fundamental understanding, but that's all that we can really tune it into something that is more valuable products.
Great. So next question. Do you guys recommend any specific extracurricular activities at university level that will be able to give you a differentiation to other students? You mentioned IChemE and JSEC.
Yeah. So I mean, I think, Tom, you would know the value of being a part of a student society, just in terms of building that professional network and seeing how other people are going about their degrees and what they're doing outside of their degrees there. So that's sort of more on the social side of things. And the professional network side of things, yeah, like the IChemE, I was part of the American Institute of Chemical Engineers as well, and the JSEC. Just sort of being a part of those societies are really important because they are professional societies, there aren't too many students involved with them. So I think that just by virtue of you participating in seminars, just asking people about what they're finding, how they're finding industry, what issues they're sort of facing, what they do, you really do stand out, and you really start to think more of a mindset of what a chemical engineer would do in industry. I think for me, I got involved with the research group very early on, and one of my goals that I would absolutely dream about every night was publishing a paper before I finished my undergraduate degree. And that was everything that I put my focus into, because I knew that that would be one way to really stand out for what my desired career path would be in terms of getting a good research, a PhD position, which allowed me to be flexible with how I focus my research. And so I think, you do have to sort of be, I think for most engineering programs in Australia or chemical engineering programs, you do have to be a part of your thesis in your final year. So it's really no harm in sort of trying to find out more about what that research group is doing and how you can get involved before your final year to really make the most out of that there.
Would you also agree that just doing any extracurricular stuff can really help you with soft skills and being able to talk to people as well?
Yeah, 100%. And I think that's one of the things as to why a PhD is so good. As I mentioned before, it's really half about your research and thesis, half about those professional skills there. And one of the things that I'm really trying to change, being involved with things like the Faculty Board of Engineering and the University Council, is to really make sure that graduates realize that a research degree or even an undergraduate degree is not just about learning the content, but it's about growing and that professional character development that you get along the way. So yeah, again, most social circles, most clubs and societies will allow you to grow in one way or another. I think actually one that particularly springs to my mind are consulting societies. I think I was a part of 180 Degrees Consulting at UNSW, where you would work in a team of 4 or 5 people. They would throw you in the deep end, giving you an industry-based program, and you had the semester to work with your team to really just come up with a solution, communicate that solution, because that's a really difficult thing to do, and think outside the box a little bit. So I think societies like that are really good on the professional development side of things that aren't engineering specifically related.
Great. So we'll move on. So to the next question. When do you all think renewable energy will replace the main source of energy in Australia? Is it possible for renewables to completely replace fossil fuels in the next 50 years? David?
No. You've got to think of the massive investment globally that's been put into using crude oil products. And basically, those infrastructure investments have to go through their lifetimes. So we're talking trillions of dollars. So it's going to take a long time before we wean ourselves of the fossil fuels. But what we'll do along the way, obviously, is make processes more efficient and integrate sustainable and renewable energy sources. But we've got a long way to go. So I can't see fossil fuels being forgotten about in our lifetime, or the students' lifetimes, maybe their grandchildren's lifetime.
Yeah, I mean, I sort of have to agree with David as well. I mean, that's the reason that in one of my sort of discussions sort of mentions that I think that we need to balance. I think in chemical industry, we might not use the fossil. I mean, in the energy side, we might not use the fossil fuel. We started to use the solar panel, but we still might need to use fossil fuels for the chemical industry. And as in 80s, you know, a lot of the times when chemical industry will produce waste. So the waste, we sort of treat the waste. So in this case that, you know, if the fossil fuel produce the CO2, we should capture it and try to utilize it, make it useful before it discharges to the atmosphere. So I think, you know, the fossil fuel is still there, but we will have a better technology in order to make sure that we can minimize the emissions of the CO2 or cycle it, as I mentioned before as well.
To all, fusion, a dream or possibility in our lifetime?
I don't think I know enough about fusion to really make that call. I hear very conflicting things about it. I would just dare to say we shouldn't put all of our eggs into one basket, so that, you know, if something like that were to work, it would be revolutionary. But at the same time, it doesn't really address all of the things that fossil fuels and alternative energies are addressing now anyway. So there's a really big distinction between, for example, grid electricity and chemical feedstocks and products that we get out of alternative sources and fossil fuels as well.
There's another question.
I don't think it will be in our lifetime in Australia. Again, it will be depends on the country as well. I think I don't see that will be in our lifetime in Australia.
Yeah, I would say fusion was a great idea 30 or 40 years ago, and it still is.
The next question, for researchers thinking about entrepreneurship, how do you protect your intellectual property when you try to sell your idea or collaborate with a company? Pretty specific question there.
How do you sorry, Rose.
No, go ahead, David, please.
I was going to say, so the question was how to protect your IP?
Yeah.
Yeah, okay, so there's two ways. There's know-how and patents. And a patent is as good as how much money you've got to protect it in the court. But yeah, I think it's very difficult to protect IP if you don't use a patent, but patents are very expensive. So it's know-how. So basically you've got to be quite secretive about how you do certain things. Like I mentioned about HTL, we've made the technology very, very simple. But without the know-how how to operate it, forget it. You've got no chance. So you can copy our design, but it will take you a long time to get the know-how.
And when you join a research group, I'm sure there's a lot of help there from people that are more senior than you in that as well.
Yeah, and universities have their IP groups, their legal departments, who will help students protect IP.
Yeah.
So there's agreements, there's all sorts of things. Yeah.
So before that, the student group talk to the companies. Normally, you will have to sign some sort of NDA agreements. Make sure that that's been signed before you can disclose anything. Even when you disclose it, you will not disclose everything. So a lot of the know-how you still don't, talk about what does it do, but you do not know how it's actually will be done. So it's those kind of things that you probably can protect.
When I say universities are very good with IP, so if a student comes up with some novel ideas, they will definitely benefit from that idea. The university share IP. If it returns a profit to the university, the students will get a percentage of that profit too. So there's lots of mechanisms in place to be fair with IP.
Yeah. Constantine, I think this question's mostly directed at you, but I'm sure everyone can give input. Beneficial IChemE student chapter activities you've joined and should be done more often.
Yeah, that's a really good question. I think sometimes the student chapters tend to fall into the trap of the doldrum of just inviting a professional and just sort of hearing what he or she has to say and then just leaving it there. I think that the more beneficial ones come from an opportunity to sort of interact with more than one person. So I think while these web seminars are great, you do really miss that face-to-face interaction. And so unfortunately, these 63 people that are here, I only see you as a name and a number. So you sort of miss that, I guess, interpersonal connection there. So I think if there's opportunities to sort of share research, share what's going on with industry, and you couple that with some sort of, I don't know, speed networking activity, or you couple that with some sort of social event or something of the like, where you can actually talk to that person and not have such a sort of power vacuum, or to me, that's very daunting to sort of just have someone to talk about everything that they're really good at. You sort of feel afraid to really interact with them personally. So I think opportunities where you can create that social interaction is really important there. I know, for example, the career fairs and the career opportunities that we used to hold with the JSEC really gave that opportunity. And it wasn't just one person that came in to talk about their career. It was usually a group of people from very different backgrounds that would really come with the pretense of just getting to know students and networking in that sense.
Great. Anything to add, Rose or David?
Not really.
Yeah, networks. So I was just answering a private message. A student had a similar question. Everybody has to build their own networks, and it takes time. But you can start building those networks as an undergraduate. Join JSEC, join IChemE, go to seminars, network. Once you get your networks, that will help you develop your careers.
Yeah, and as an undergraduate, I hated the term networking, and I found it so difficult to go up to people and have that sort of forced interaction with the purpose of building a network. And what I sort of discovered over getting more used to building those networks is that a lot of the time it just comes naturally with being involved in certain things. So it doesn't mean that you have to go and you have to force a silly question to someone for them to get to notice you, because frankly, they probably won't remember you anyway. It's just about being regular and being there, and just by virtue of being involved, you slowly build that network over time. You don't have to force yourself through it. And it will eventually come, and I promise you, and I was so skeptical about this as an undergraduate, it will benefit you one way or another. I don't know how yet, but it will somehow.
Yeah, the network is also, as Constantine said, that they might not remember you, but it's actually build your confidence. Build your confidence in terms of to be able to really sell your ideas, sell yourself in terms of your skills. So in interview, and sometimes you might think that they do not remember you, but a lot of the time they still remember you, because and that's very important in the future. Is, sometimes it's who you know is also as equally it's important of what you know, because that will actually open a lot of doors and avenues as well. So I think that when you still young undergraduate students go out there, mingle with the industry, I mean, they will remember you. I mean, I remember Con when he was a second-year student, so I still remember him now. So it is, I mean, it is important, the networking.
So unless you guys had any questions for each other, I think we've answered all the ones that have popped up. Good. None spring to mind. Well, thank you everyone so much. I'm sure everyone took away a lot from today's session with regards to future energy alternatives and more sustainable use of our own resources and pre-existing infrastructure here in Australia. I'm sure everyone agrees that having Professors Rose, David and Paul and Constantine here to share their insight into the future of chemical engineering has been invaluable. So I'll just thank them all again for their contribution. So I'll just finish off today with what's coming up later in the week and tomorrow. So tomorrow we have the pharmaceutical industry talks. Two streams, the first one on biotechnology and pharmaceuticals, and the second on the same topic. We're joined by Professor Vogel Hessel, University of Adelaide, Russell McGifford, the Cannabis Group Limited, CAN Group Limited, Professor Charles L. Cooney, co-director of the program of the pharmaceutical industry at MIT. And in the other stream, we have Hayley Scarborough from PFSA, Andrew Hislop from CSL, Vin Dung from Maine Pharma, Associate Professor Matthew I. Hill from Monash, Associate Professor Keith Chappell from University of Queensland, Professor Jason McKenzie from the Peter Doty Institute for Infection and Immunity, and Tim Veal from GlaxoSmithKline. There's a range of panels and technical talks relating to the COVID pandemic and how the chemical engineering industry has helped with that. And then also later on tonight, starting in, I believe, an hour, I might be wrong, we have trivia, which you can still register for, where we'll be hosting a Kahoot session with some fun questions relating to chemical engineering. So I hope we'll see you all there later. Thanks, everyone.
Thanks, everyone.
Thanks, Tom. Thank you, everybody.
Thank you.